In this session, we're going to solve basic logarithmic equations. But before we get to that, we're going to explore converting equations between exponential and logarithmic form. First, we're going to write logarithmic equations as exponential equations. And our first example is log base 3 of 81 is equal to 4. Because there aren't any variables in this equation, it's not that we're going to solve anything. We're just going to see how we can interpret a logarithmic equation. What's the base? It's 3. And a logarithm is an exponent. Therefore, we can rewrite this equation, log base 3 of 81 equals 4, as the base 3 with the exponent of 4, which yields a result of 81. This is an exponential equation now. Next, log base 1/2 of 32 is equal to 5. What's the base? 1/2. And a logarithm is an exponent. And so we can write 1/2 as the base to the negative 5, which is the exponent, and that yields a result of 32. Now we're going to perform the operation in reverse, writing exponential equations as logarithmic equations. Our first customer is 2 to the 4th is equal to 16. So I'm going to write this as a log. And what's the base? 2. The exponent is the logarithm, so that's on the other side of the equation. And the result is 16. So that's where all the pieces go. Log base 2 of 16 is equal to 4. That's an equivalent equation. Next, we have 10 cubed is equal to 1,000. Since the base is 10, we're simply going to write log. And the log, in this case, of 1,000, the exponent on 10 that gives me 1,000, is equal to 3. And so log of 1,000 is equal to 3 is an equivalent equation. Our next one's a little more interesting because it doesn't have numbers so much. Well, it's got one. W to the x plus 2 is equal to r. And so I first want to think about what's the base? W. So I'm going to write log base w. R is the result. It goes into the argument of the logarithm because a logarithm is an exponent. And so the log is equal to x plus 2. And so log base w of r equals x plus 2 is an equivalent equation. And we're going to use this kind of conversion process to solve the equations in this session. There will be more interesting ones down the road, but these ones are basic, hence the title of the video. Okay, now we're going to solve equations. The first one being log base 4 of x is equal to 1/3. So first I want to write this as an exponential equation. What's the base? 4. A logarithm is an exponent. So the exponent is 1/3. And this equals the result, x. 4 to the 1/3 is equal to x. That kind of sucks. We could leave it like that. If you wanted to, you could say that x is equal to the cube root of 4. I don't know that there's a lot to be gained for doing that, but I'd take either one. Next, we're looking at 5 to the 3 minus x is equal to 12. This is an exponential equation. I know. We're going to convert it to a logarithmic equation and then see what happens. So I'm going to write down log, and then the question becomes, what's the base? The base is 5. Log base 5 of 12 is equal to the exponent, because a logarithm is an exponent. And so we have log base 5 of 12 is equal to 3 minus x. Now I want to solve for x, so I'm going to add x to both sides and then subtract the logarithmic expression from both sides. And if you need to, pause the video and double check my work on this. But x is then equal to 3 minus log base 5 of 12. There's not a lot I can do to clean that up at present. We're going to see how we would get a calculator answer from that down the road. But for right now, that's good enough for us. Next, continuing to solve equations, we have log base 3 of 2x is equal to log base 3 of 24 minus x squared. If we think back to the graph of, let's say, y equals log base 3 of x, it being asymptotic with the y-axis down at bottom and curving up to the right, it's a one-to-one function. What that means to us is that if the expressions are equal, then the arguments are equal. Hence, we can say, because the bases match, that 2x is equal to 24 minus x squared. This is a run-of-the-mill quadratic equation. Getting everything on the same side and setting the equation equal to 0, we get x squared plus 2x minus 24 is equal to 0. And so x plus 6 times x minus 4 is equal to 0. And so x is equal to 4 or negative 6. Hold the phone. The argument of a logarithm cannot be negative. Remember, the domain of a logarithm is positive numbers. And so x equals negative 6 is a problem for log base 3 of 2x. It, by the way, is also a problem for log base 3 of 24 minus x squared. Only one of these would have to have the problem, though, for us to say, nope, negative 6 doesn't work. Ultimately, our answer is simply x equals 4. Next, we have log base 4 of 8x plus 10 is equal to 3. Now we're back to converting this to an exponential equation. What's the base? 4. A logarithm is an exponent. So we have 4 to the third is equal to 8x plus 10. Now hopefully you're starting to see the benefit to converting between these two forms of equations. 4 cubed is 64, so we have 64 is equal to 8x plus 10, and so 8x is equal to 54, and so x is equal to 54 over 8. I wouldn't want you to leave it like that. I'd want you to reduce it. And so how about if we say that x is equal to 27 over 4? That works for me. Alternatively, if you really wanted to, you could say 6 3/4 is what x equals, but I don't need you to do that. What I do need you to do is double check this in the argument. Make sure that the argument of the logarithm, in this case 8x plus 10, doesn't become negative from our solution, because if it does, you gotta ditch it. In this case, x equals 27/4 works, and there we go. Next up, we have the equation log of 2x plus 3 is equal to 1. Since it's just log, the base must be 10. And so we have 10 to the first power, because a logarithm is an exponent, is equal to 2x plus 3. And so 7 is equal to 2x. And so x is equal to 7 halves. Another quick little check, make sure 7 halves doesn't make the argument 2x plus 3 a negative number. And it doesn't, so we're good to go. If you're thinking that these equations aren't so bad, you're right. The ones down the road, going to be more interesting. The one down the page, natural log of e to the 2x is equal to 8. Natural log means the base is e. The exponent is 8. And so we have e to the 8 is equal to e to the 2x. And hey, the bases match. That sounds like something we've done before. So 8 is equal to 2x, and so x is equal to 4. Beautiful. Now we're going to turn our attention to some applications. The formula d equals 5e to the negative 0.4h can be used to find the number of milligrams d of a certain drug in a patient's bloodstream h hours after being administered. When the number of milligrams reaches 2, the patient gets another dose. What is the time between injections? Before we get to that, I want to point out that d equals 5 times e to the negative 0.4h has the form a equals p e to the r t. Yep, that one's coming back. So we're using that equation, but here's the deal. We're told that when the number of milligrams reaches 2, then the patient gets another dose. Find the time. In other words, find H. The number of milligrams was represented by D. So to flesh this out, we have that 2 is equal to 5e to the negative 0.4 h. And now we want to solve for h. Here are our steps basically. First, isolate the exponential factor, in this case e to the negative 0.4 h. Then deal with the fact that we have a variable and an exponent. So the first thing I want to do, divide both sides by 5. So we end up with 2/5 is equal to e to the negative 0.4 h. And now, since I have a variable and an exponent, I'm going to use a logarithm. You see, because a logarithm is an exponent, I'm going to end up with an expression that has log equals, exponent. What a shocker. What's the base? It's e. With a base of e, I'm using the natural log. So the natural log of 2/5 is equal to the exponent of negative 0.4 h. Now, since I want to solve for h, I just need to divide both sides by negative 0.4. Now, when I put natural log of 2/5 in my calculator, which I'm about to do because we have now isolated h, I need my calculator to know that 2/5 is the argument. So I should put that in parentheses. First, the exact answer is h is equal to the natural log of 2/5 divided by negative 0.4. Let's go for a calculator value though, because I'd have a hard time looking at my watch and figuring out that much time had passed. And my calculator is telling me that h is approximately 2.29 hours. Now again, that might be tricky to look at my watch and figure that out. And so we can interpret this as 2 hours and then 0.29 of an hour, right? 0.29 of an hour, which means we can take the 0.29, multiply it by 60, and get that h is approximately 2 hours, 17 minutes. So I'm going to call that 2:17 hours. I personally would take 2.29 hours, but in the real world, you might need to know that it's 2 hours, 17 minutes. Next, according to the CIA World Fact Book, the population of the world in 2014 was about 7,175 million. What kind of number is that? Folks, that's billions. So 7.2-ish billion. And growing at a rate of 1.064% per year. With that growth rate, by the way, the World Fact Book says that's about 2.4 new people in the world every minute. It sucks to be that 0.4 of a person. Anyway, sorry. At this growth rate, P of t equals 7,175 times 1.01064 to the t minus 2014 represents the population in millions in year t. According to this model, when will the population be 12 billion? We want to know when the population will be 12 billion. That population is the P of t. This is like PERT, but not quite. This is more like compounding interest, discretely compounding interest. In any case, we want P of t to be 12 billion, but our number was in millions. So 12 billion is actually 12,000 million. I just need to convert that because of how the numbers were given to me. So what we're looking at is 12,000 is equal to 7,175 times 1.01064 to the t minus 2014. Before we go on, let's just talk about this a little bit. The 1.01064, the decimal portion is actually the decimal representation of the growth rate of 1.064%. And the exponent, the t minus 2014, means that if we had, say, t is equal to 2020, then the exponent would become 6. You see, this is just saying it's the number of years since 2014 that will be the exponent. In any case, now our steps are the same as before, the broad strokes anyway. That is, isolate the factor that has the exponent, and then deal with the fact that we have a variable in an exponent. So we're going to divide both sides by 7,175. And I'm going to leave the fraction on the left like that. So 12,000 divided by 7,175 is equal to 1.01064 to the t minus 2014. Now this is about to be really weird, because what's the base? 1.01064. That's going to be lousy to write. Oh well, we're going to write it anyway. Log base 1.01064 of 12,000 divided by 7,175 is equal to, what is it equal to? Well, remember, a logarithm is an exponent. And so it's equal to t minus 2014, which means that t is equal to 2014 plus log base 1.01064 of 12,000 divided by 7,175. We are going to find out how to do this using a calculator down the road, but for right now, just in case you're on pins and needles wondering when the population will reach 12 billion, it'll be sometime in the year 2062. Looks like it's going to be in about July. In order to do that from the calculator, by the way, what I did was I used what's called a change of base formula. And that's how I dealt with the logarithmic expression. You're going to learn that down the road. If $8,000 is deposited into an account that earns 4% interest, compounded quarterly, how long will it be before it's worth $10,000? Compounded quarterly, I remember that guy. That means that n is equal to 4. There was this formula that I remember. A equals p times the quantity of 1 plus r over n to the nt, where n is the number of times that it compounds per year. If this were a test question, by the way, I would include the formula on the test. You don't need to memorize it. However, you do need to know how to use it. And here's the deal. We want to know when the amount is going to be $10,000. If we have a principal investment of $8,000 and the interest rate is 4%. So plugging these numbers in, I get 10,000 is equal to 8,000 times the quantity of 1 plus 0.04 over 4 to the 4t. Did you forget to express the rate as a decimal? I hope not. Our broad strokes are the same as before. Isolate the factor that has the exponent, and then deal with the rest of it. In order to do that, we're going to divide by 8,000 on both sides. And so 10,000 divided by 8,000, and that reduces to 5/4. So we get 5/4 is equal to 1.01, which is what that parenthetic quantity becomes, to the 4t. And now we have a variable and an exponent. Enter a logarithm. What's the base? It's 1.01. So we're going to write log base 1.01 of 5/4 is equal to 4t. And so t is equal to the log base 1.01 of 5/4 divided by 4. Let me make clear that 5/4 is the argument, and my calculator tells me that this is about 5.6 years. I know it's not really fair. You don't know how to get this answer out of your calculator, and I do. I'm not bragging. I'm just trying to drum up some interest for when we get to what's called the change of base formula, which will allow you, yes, mortal humans, to compute expressions like that. In any case, about 5.6 years. How long will it take to double? The process is really the same. Instead of it being worth 10,000, it should be worth, well, if it started at 8,000, 16,000. I'm going to write this down, though, because I want you to see an important aspect of it. And so the formula fleshed out would be 16,000 equals 8,000 times 1.01 to the 4t. And again, broad strokes are the same. We're going to divide both sides by 8,000. And when we do, on the left-hand side, we end up with 2. And so 2 is equal to 1.01 to the 4t. The rest of this finishes off the same way the other one did. But check this out. The 16,000 over 8,000 is equal to 2. That would work even if it was 1,600 over 800. It would work if it was 2 million divided by 1 million. The time it takes to double is irrespective of how much was originally invested. Well, just so you don't wonder too long, the same steps we just saw would indicate that t is equal to the log base 1.01 of 2 divided by 4, and my calculator tells me that it would take about 17.4 years for this investment to double. The next one, though, how long would it take to double if the interest is compounded continuously? That mere mortals can do. Compounded continuously means we're using a equals PE to the RT. And so we want to double. Check it out. If we're doubling, then the amount we have, if we started with P, is going to be 2P. That's what it means to double. So it doesn't matter how much was put in. What does matter is the interest rate, which is 0.04. And so we have 2P equals P times e to the 0.04t. When we divide both sides by p, the p divides out of both sides. It's amazing how that works. And so we have 2 is equal to e to the 0.04t. This is looking a lot like before, except the base is e, which means we get to use the natural log. And so we get that the natural log, because the base is e, of 2 is equal to, remember, a logarithm is an exponent. So 0.04t, and solving for t gives me that t is equal to the natural log of 2 divided by 0.04, which my calculator tells me is about 17.3 years. Okay, so not a lot different than the 17.4 that we just saw, but hey, a tenth of a year is a tenth of a year, right? Last, and certainly not least, the half-life of uranium-235 is 703,800,000 years. Something tells me that there's been some rounding off. Use this to find the rate of decay of uranium-235. You may remember that A equals PE to the RT is a formula used for radioactive decay. The half-life is the time it takes for half of the radioactive material to decay. Let me emphasize one thing. Half-life is time. So the time is going to be 703,800,000 years. As far as half-life, just as it didn't matter how much was invested before we could figure out the doubling, it doesn't matter how much we have for us to figure out the half-life. Because if I have an amount P to begin with, then half of that would be half of P. That is what's going to go on the left of the equal sign. So I get 1/2 P is equal to PE to the 703,800,000 times R. And what we have now is a variable in an exponent. Broad strokes, same as before. Isolate the factor that has the exponent. And so in this case, we are going to divide both sides by P. It goes away on both sides, and we end up with 1/2 is equal to E to the nice round number of 703,800,000 times R, and because this base is E, we can use the natural log. So the natural log of 1/2 is equal to 703,800,000 1,000. Why did I use this one? I could have used one with a shorter half-life. I mean, really, some materials have a half-life that's like a day or less than a second. Anyway, times r. And so we are now going to divide by that coefficient. I don't want to say it again. Okay, fine. I'll just say it one more time. So r is equal to the natural log of 1/2 divided by 703,800,000. That I can put into my calculator. I swear my calculator just went, why'd you use this number? So r, my calculator is telling me r is equal to negative 9.8, I'm going to say round off, 9.85 times 10 to the negative 10. What the heck does that mean? Okay, interpretation. The negative, that happened because it's decay. You see, we aren't talking about population growth, we're talking about radioactive decay. The 9.85 times 10 to the negative 10, this is a percent expressed as a decimal. And so if I multiply by 100, then we can get that the rate of decay is about 9.85 times 10 to the negative 8% per year. The decay is where we're reflecting that the answer was negative. What I want you to get most from all of these examples is that while exponential functions help to describe a lot of situations, if a variable is in an exponent and we need to know what it is, the logarithm is how we get out of that mess.